how the graph class looks like is, we will have a constructor of the graph which will just say that we have a graph with n nodes and all these edges. Currently all the edges are there. Now add edge will just say that okay, right now I'm adding an edge just in that existing graph. In the existing graph I'm adding a new edge. I'm just adding a new edge. Cool. Now shortest path will just say, just give me the shortest path between or from node 1 to node 2. You just have to return that. So you can just get this things called, which means graph will be just called one time, add edge can be called n number of times, and shortest path can be called m number of times. I just have these naming conventions. The big N is actually saying that I will have n calls for add edge, and big M is saying that I will have a call to shortest path m times. Now for just to have a simplicity in the entire code, we will use V as the number of vertices, E as the number of edges, N as the add edge number of calls, M as the shortest path number of calls. Now as you can see the problem statement itself, now we will have a graph in which you will be given the number of nodes and the existing number of edges. Now and I can just eventually start calling the shortest path, which will actually give me sorry, it should be up till here. This is the entire graph up till here, this point. Right now shortest path will just say okay, give me shortest path between 3 and 2. Again shortest path, it give me a shortest path between 0 and 3. Add edge, just add an edge from 1 to 3 with a cost of 4. Now again shortest path, give me a shortest path between 0 and 3. Now this is how it would look like. Again as we saw that we will name this as a V, which is the number of although we will have input as n, but in our complexity analysis we'll just say V is the number of vertices, E is the number of edges for us, right? These number of calls are actually n, as we saw. These number of calls for shortest path actually m. Now the big thing is in this problem is that all V, N and M all are equal, so it might not affect you in the complexity wise, that if I ask you that okay, that just go and compute and find the shortest path for, let's say if I just do a add edge function. Now it will highly depend if I just try to say okay, let's say if I just modify my question entirely and say M is actually 1000 or like 1e4, then the approach which you will take will change. So we will discuss all the approaches. Now M is just saying just find the shortest path. Now if I just try calling shortest path many number of times, so for sure I will have to do some pre-computation. Now let's say if I just say okay, the shortest path is very small, like I'll just call shortest path just 10 times. Right, so I just say it's better that I will just compute shortest path again and again. Instead I would have might said okay, I will call add edge, let's say 1e4 times. Then you would say okay, now I'm adding edge many times, so there should be a like algorithm used in which add edge is not impacting much, right? Now in other case it can be that add edge is not impacting much, while shortest edge might impact, but the calls are less, so it would not affect me as such. It would affected me in add edge function. So with this kind of changing constraints, because constraints are both same in this, but interview might ask you anything. So with this change of constraint, we'll see that how we can solve it. Again, it's just a shortest path problem, that you will just have a graph, you will just simply add an edge and again find the shortest distance. Shortest distance to find between two nodes, we just simply, efficient way is simply using a Dijkstras. Dijkstras, if you don't know anything whatsoever algorithm I'm going to tell, no worries at all. We are actually explaining everything. No worries if you know it, don't know it. It's just that we'll just try to see how we actually reach to a point that okay, we can get to know it's a Dijkstras. Indirectly you might be applying Dijkstras, Floyd Warshall, anything like that, but still it might happen that you might not know its name is Dijkstras. Cool. Now let's simply see that okay, that if you want to find, and it's a very standard algorithm, so let's go jump out of it. If we want to find the shortest path between nodes, which are 2, so we can just simply use a Dijkstras algorithm. Now in that Dijkstras algorithm, now we'll go on to this complexity analysis like later. It just happens that first simply we build the graph. Now for sure we have a graph, we usually build the graph via adjacency list. So what I will do is I just simply build the graph via adjacency list. Now when we have another cost as, so how we build the graph as okay, the node which is the u node to actually a pair, saying it is a v node and it is a v node and also the cost from u to v. Now it can happen that I have a v2 with a cost t2, which means from U to the V2 node to cause C2. So it's just an adjacency list. So we will have int here and a vector of pair here. That's it. Cool. It is how we represent the graph. Now, when this is done, okay, again, you will have to find the shortest path. Now, again, for shortest path between two nodes, which is actually given, you have to find the shortest path between 3 and 2. Now, if you know Dijkstras, you can just skip this part. Now, if you don't, it simply happens that you will start from a node. Now, if you want to find the shortest path, so greedily take the shortest path itself. If I start from a node, which is actually, I will just keep track in my, now, if I want to take the shortest path itself every time, so I need to keep track of it, like I need to keep track of that node in a data structure which is having shortest path itself. So I will take, okay, shortest path, which means the minimum path which means min heap. So to keep track of the shortest distance, I will use a min heap. Now if I want to use a min heap, I know initially I am at node 3 because I have to go from node 3. Now ultimately, if I reach in the shortest possible path to node 2, I will always travel on the shortest possible path. So anytime I reached node 2, I will say, okay, I have reached node 2 and I have traveled via the shortest possible path itself. If I am at node 3, I will say I am at node 3. Currently distance up till is actually a 0. So this will be say distance. This is actually the node at which I am at right now. I was starting from node 3 itself, so the distance was actually 0. Now again, by the concept of priority queue, this is something inside my priority queue right now, and I will always take the shortest distance because I want to greedily traverse my shortest distance. I will take the distance 0 and ultimately I will just pop it out from the priority queue. Now I will try to go on to all its neighbors. It has just one neighbor, so I will say, okay, distance from 3 to 3 was 0. It has only one neighbor. So now the distance to you, bro, 0 is actually 3 plus 0, and I'll put this in my priority queue. So now this will go away from the priority queue and a 3 comma 0 will come in. 3 saying is the distance, minimum distance right now, and 0 is saying, okay, the node. Now, okay, again, it is the only element of the priority queue, so it will just pop out. It's as soon as it pops out, it has again 2 neighbors. So to go to 2, it will say I have a distance of 3 plus 5. To go to 1, I have a distance of 3 plus 2. Now to go to 1, okay, it will just push in both. It will push in 5 comma 1. It will push in 8 comma 2. Again, it's a priority queue, so it will take the minimum distance out. It will take this bro out. So this has been done. This has been done. It will take this out from the priority queue. 5 comma 1 has been got out from the priority queue, which means this has been visited. Now again, for this it has only one bro, so it will just go and say, okay, up till me it was 5, so you will have a 5 plus 1 comma 2. Okay, cool. I will just remove it out and I will just push in a 6 comma 2. Cool. This is also visited. Now again, it's a priority queue, it's a min heap, so it will take the minimum element out. Minimum is actually a 6, so it will just grab this out and say, okay, 6 is the minimum distance to you. Okay, cool, bro, up till you is the minimum distance, which is actually 6, and then I just mark your distance as 6 and simply node is 2. Oh, node is 2, I had to visit a 2. Great, bro, great. You have reached the final node. Just simply return that distance itself. So this is the distance for node 2, which is the minimum distance. You saw that 8 was never used because it was a larger distance, and I'm greedily going to do always the minimum distance possible. And that is how simply a priority queue works. Simply pushing in the distance on the node and grabbing out the minimum distance every time and then computing the final answer. As soon as you reach your node 2, you have got your answer. Cool. With this concept, you can just simply see that I will just find the shortest path between from like this initial node, which is 3, and as soon as I reach a node 2, I just get the answer. The only thing is that you keep track of the distance and the node inside the priority queue. And again, if I just go and find the shortest path from 0 to 3, again the same procedure as we discussed above will actually apply. And again, for this you saw that we are using a priority queue and we can have E edges. Now in the priority queue, I can only have V node, like I can only have these nodes. So the total complexity of actually priority queue is V plus E log V. So that would, if you just go and look back, I've also mentioned that it's actually very standard, but if you don't know, I just told you. Now what if I added an edge? So you will see that I added an edge here. So nothing much will change. In your graph, you had an adjacency list. So what you will do is, in your adjacency list, you will have a graph 1. You just push back another pair, which is actually a 3 comma 4, just saying a node 3 with a value 4. It is just simply what you will push back in your graph. So that's a O of 1 operation for this particular one call of add edge. Now again, if I want to find a shortest path between 0 to 3, I'll again start my Dijkstras or simply a greedy traversal using min heap from 0, and then I'll try to reach my 3 here itself, and that would be my answer, which is actually 6. Cool. Let's quickly jump onto the code itself. Or why I'm jumping on the code right now and not discussing the other approach, because you will see that I will firstly discuss the time complexity, and I will show you that in what cases it is beneficial and in what cases it is not, right? So let's quickly jump onto it. I will just have usually we write the code in the editor itself, but it's a big video, so we thought let's discuss the code, and it's a very simple code of Dijkstras, and I highly recommend don't watch the code. Firstly, try the code by yourself of Dijkstras and try both the codes, which I'm going to show the other approach also. For Dijkstras, simply usually how I do graphs is like adjacency list is from integer to actually a vector of pair of vector of pair of ints, or you can also have a simple 2D array also saying from integer to actually vector of pairs of ints. Cool. So ultimately I also want to have an n, so I initialize that as a global variable. I went onto my entire graph, initialize my global n to actually internal n, and then I went on to all the edges, and as it is the directional, so I just simply said okay, from edge u to edge v with a cost of c. So I just simply plotted this out. Now when this is done, again this portion of graph initialization is done. Now as you are simply initializing the graph, you know that the complexity is nothing but total number of edges, which is actually e in your case, or if in worst case, if it actually you want to initialize all of these graph, which means let's say in my edges, let's say I have said okay, n nodes are let's say 10, but my edges are let's say 2. So still I will have some dangling 8 nodes, right? So for those 8 nodes itself, you can just initialize here itself by the empty vector, or in the map or a normal map, it is not required as such. So for you right now, it will be O of E only, but in general case, if you use a vector, then it will be O of E plus V, which is actually true. Cool. Now space is also O of E plus V, because for sure you are actually using those E edges, or in worst case those V nodes. Cool. Now if I do an add edge operation, simply just inserting that node in the priority queue itself, you will see that for one insertion the time and space both are O of 1, but for n insertions, because I told you that add edge operations are n times, so that will be O of n for like total n operations. Now again, shortest path, as we saw earlier also, it's just simply using a priority queue, but it's a min heap. So I'll take a pair. This pair says it is a distance and the node. Now why the distance is at the first? Because I want to sort my priority queue, or basically take the minimum distance pair from the priority queue out, so I have to keep the distance in the front. Cool. Now I will have the distance array. Now this distance actually makes sure both the things. If that is not that node is already visited, if yes, then if it is visited with a minimum distance. If it does not have a minimum distance, so you can visit that node again, right? It just shows this that okay, if you want to visit that node again or not. Now I will just initialize it as you do in a simple queue or in a BFS, that you just simply go and push that element in your queue. So I'll just push that distance and the node in the queue, and also mark okay, for the node 1 the distance is actually a 0. Again, as you do in a simple queue, you just do it empty. You just get the first node out and the current distance out. You will just simply remove it from the queue, and then you will just check if the current distance which you have got is actually more than the existing distance what he has already, that node has already. So it's of no point to actually process that. So please continue. You don't have to process that, because you already have a lesser distance. If you are giving me more distance, why would I take it? I'm a greedy person. I'll take always less. So if I have less, I will just ignore you. Now as soon as I said okay, if I reach the node 2, oh bro, well done, I will just simply return that current distance, as you saw in the example itself. Now I'll just simply go on to all my neighbors. I'll just check if the distance to you, bro, if the distance of my neighbor, if it's actually what I'm trying to give him is, I'm trying to give him my distance plus the edge distance from node to the neighbor. I'm trying to give him this. Now he's saying that if his distance, his existing distance, if it is more than this what I am offering, it is what I am offering. It is what he has. So only if he has more distance, then only he will actually accept my offer which I am giving him. So my offer is this. He will accept only when he has a more distance than me. If we had a less distance than me, then he would have not even listened to me, right? So that's the reason. He had more distance than me, so he listened to my offer. Now my offer was the new distance, which was actually current distance plus the edge cost between me, which is the node, and the neighbor. So that is this cost, and then I'll just simply update my neighbor's distance to the new distance which I am offering to him, and then simply push new distance and the new neighbor node first. Ultimately, if let's say in whatsoever case it could not reach this, so it will simply return a -1. Again, the time complexity for this is O of v plus e log v for a simple Dijkstras algorithm, but this will be called m times shortest path number of times, which is m times. So that's the reason again a m factor was added in the picture. Space is nothing but O of e plus e, because no matter m times or what, still the space will remain constant, which is actually the graph space which you actually used, right? So that will be of for you. Now in this sorry, I just missed one thing, that for sure you will have a heap, as you are using heap, and in a heap you can actually push in the e index e edges. So for that you will have your heap as e, and you will have distance which is actually initialized with n nodes, and n we actually mentioned that we will have v vertices, so that will be O of e plus v. Now you will easily see one worst thing is in this is okay, let's say my e was let's say 100, that's good, okay, cool, no worries. My v was let's say also 100, that's also good, okay, but e was actually, you saw that, okay, it was actually not exactly 100, but n into n. If I just go back and look at it, it was actually O of n into n. So edges can be more, and the edge length, and it is same, it is 3, but edge cost, and it can also be your 1e6, but it can be around 1e4, right? Okay, so it can be around 1e4. If I just go back, it can be around 1e4. That log of 100 is actually very small number, so that can be 1e4, that can be 100. This is actually right now with number of calls to shortest path is actually 100, so that is gonna work. Okay, 1e6 is gonna work. But let's say if I asked you, bro, what if I just tell you number of calls to m, which is shortest path, will actually be high, which means number of calls to shortest path will actually be, let's say, 1e4. So this code would never work, because this is okay, this is entirely okay, no matter how high your e or v goes, no matter how high your n goes, again, no matter how high your n goes, still if the n is actually again 1e6, still it will work. Again, remember this fact, still it will work, because the next approach which we're gonna see, it will not work in that approach. So that's the difference. In the interview, he might direct you in any of the ways. So in this approach, it will work. Very high n, it will work, but very high m would not work. Sorry bro, I'm really sorry. Now for that, the interview will ask you a follow-up. Cool. Now again, you saw the total complexity is n plus m into v plus e log v. This portion is because of shortest path, this portion is because of add edge. Now space is again e plus v plus n. Again, it's for priority queue, it's for actually the number of nodes, and it is actually also for initialization, so it's just mix e plus v plus e plus v plus n, right? So it's a total space. Now, and we saw that if we had a high m, it will not work. For high n it will work for sure, but for high m it will not work. So we'll look for the other approach. Now why high m was not working was I was computing shortest distance again and again for every node. What if I ask you, like again, for m equal to 1e6, it will never work. Now the next approach, it will work. Why the next approach will work? Simply don't think of the algorithm itself, just think of what you need. You need some pre-computation. Now for that, you will need to pre-compute the shortest distance between every possible node pair. For that, you can simply use, if you just imagine your entire node pair, which means node 2 to node 0, node 1 to node 3, this will actually be the cost, this will actually be the cost. So you can just imagine the entire graph as a matrix itself, right? And just simply say, okay, the value, as you can see, adjacency list is just simply representation, adjacency matrix is just simple representation in a grid for the graph. Just simply think that, okay, that can be adjacency matrix for us, and then in the matrix values I will actually keep the shortest possible distance from the node u to node v. So that is how we represent graph as a matrix. in this, the thing which we will do and we'll make sure is we'll actually pre-compute the shortest distance between every node. As soon as I will just initialize my graph, I'll just find the shortest distance between every pair of node, and that is internally called as the Floyd Warshall algorithm. You will see, no worries if you know, if you don't, no worries at all. Simply we will see. Now initialize, we will have this graph. For sure we'll have to do some initialization. Now we are keeping the distance, so by default every value of this particular matrix will actually be an infinity, because that is the minimum distance. If it is not even reachable, what is the point of minimum distance? It will be infinity, which is 1e9 for us. Now why not int max? Because if we just add int max plus int max, it will overflow. So we just took a value. If even if we add a int max, which means 1e9, if I even add a 1e9, it will not go beyond 2e9, which is actually, it will not go beyond int max. Int max is 2e9 plus something, right? Cool. So what I will do is I will have my graph, I will initialize my graph. Now initialize your graph. Simply, you have this matrix, simply populate this matrix while initialization. So what I will do is I will just simply initialize this matrix. Now for sure, between node 0 to node 0, which means from me to me, the distance is 0. So I'll just simply mark a 0, 0, 0 and 0. That is from node u to node u. Now from 0 to, now as you can see, I have the edges from 3 to 0. I have an edge of cost 3. That's a decent cost. So from node 3 to node 0, I'll just add a cost of 3. Cool, no worries. Again, the same thing I'll just make sure I'll do for other nodes, which is actually node 0 to node 1, node 0 to node 1, cost 2, node 0 to node 2, cost 5, node 0 to node 2, cost 5. So by this, I'll just simply plot all the edges which I have right now. Now when this part is done, will come as how I should minimize the cost. That how okay, I have got this. Now how I should find the shortest distance from node 2 to node 3. Simply, the only thing which you have to do is try and utilize other nodes to be an intermediate between u and v, which means earlier I had an edge from u to v, and that was the cost which you were incurring right now. Now just try to find another node, let's say k. This node k will be the intermediate, and you will see that if you have this c1 and this c2, is it possible to have this c1 plus c2 less than your current c? This is what you are trying to do. So you are trying for the intermediate nodes, and for that intermediate nodes you are trying to minimize that distance. Again, I will try for all the intermediate nodes. Intermediate nodes can be 0, 1, 2, 2 and 3. I will try for the first intermediate node 0, then 1, then 2, then 3, or you can just try that in any order. It's just that you have to minimize the distance. Now if you're just doing that, just make sure that if you're just keeping the array and minimizing the existing array, which means I'll try for all the possible combinations, which means as you saw that I have a u and v, so I'll try all possible combinations of u and v. It can be from 0 to n, it can be from 0 to n, right? 0 to n, because I have n nodes. So I'll try to minimize all possible combinations of u and v with this node k. Now k, I am just trying for k equal to 0, k equal to 1, k equal to 2 and k equal to 3. So I'll try to minimize for all pairs, which is u and v. Now for, I'll just say I and j, so I'll just try to minimize I and j's value. For when I say minimize, I'll just keep track of the minimum value existing also, and then I'll just say, okay, from this node I will hop on to a node 0, and then from node 0 I'll hop on to a node j. That's what I was doing. From node I will hop on to a node 0, because k is 0 right now. As you see, k is 0 right now, k is 0 right now, and from node 0 I will hop on to a node j. This is how I can minimize the distance from node I to node j, and I'll try for all the pairs. Again, mark my words, for all the pairs, because I just want a minimum answer for all the pairs. Now just as an example, you will see that you have a distance from 3 to 2 as a distance 8. As you saw is also from 3 to 2 distance was 3 plus 5, which is actually 8. Now you had to minimize this distance. So what you did was you tried the node 0 as the middle node. Distance was existingly 8. You tried 0 as the middle node. So I will go from 3 to 0. Distance incurring, I will get a 3. Then from 0 I will get to a 2. I'll incur the distance as 5. Okay, cool. I got this distance as 8. That is true. Now if I am using a middle node as 1, what could have happened was I will now instead use a middle node as 1. Okay, cool. From 3 to 1 I will use a distance of 5. and from 3 on from 1 to 2, 1 to 2 I'll use a distance of 1. So 5 plus 1 is actually 6. So you saw that when you will go on to the next middle node, it actually reduced your distance. Again, you can see the other example as from 0 to 2 the distance was 5, from 0 to 2 the distance was 5, simply, right? Else, what if I'm saying if I just use the middle node as a one node, because as you're gradually going to all the nodes and you're just minimizing the distance. So from 0 to 2 the minimum distance was actually 5. Now I'm saying, okay, I'll just use 1 as a middle node. From 0 to 1 I used 2. Okay, I have the current cost as 2. Now from 1 to 2, from 1 to 2 again my cost is 1, so plus 1. So you will see the cost reduced to 3. So this is how you can reduce the cost and try for all the middle elements. So you will try for all these k middle elements and for all the pairs. So just have a condition that for all k, for int k equal to 0, k is less than n, for int k equal to 0, for int k equal to 0, k is less than n and k plus plus, just simply do this thing. Rather than 0 you will put a k, rather than 0 you will put a k, and that's the only thing how you can just get the minimum distance between all shortest possible pairs. Now again, Aryan, okay, you just found all pairs for all the middle elements, right? Now what if I add a new edge? So here you saw that you added a new edge. In the last you saw that your final matrix looked like this. It was the same matrix which was after trying on all the possible middle elements. If you add a new edge, so that new edge can also act as a middle node, obviously, right? Obviously. So because earlier you were trying for all the middle nodes, right, and trying for all the pairs, minimize for all the pairs considering that middle node. Now I'm saying, okay, if you add an edge, so I'll consider that edge itself as a middle node. So if you added an edge, let's say from u to v, and earlier I was trying, okay, for I to j, I was trying for all middle nodes k. That is what I was doing. I was trying for I to k, then k to j. It was what I was doing earlier. Now if you added an edge u to v, then I will try what? I'll try for all the ij combinations considering u as the middle node, which means I'll just say I to u, and then u to v, I know the cost is c, which you are giving me, which is actually 4, and then from v to j, I'll say, is it giving me minimum or lesser distance than what I already had from I to j? If that is the case, good. If not, then simply you can just continue with your existing values. So this is how new edge added can actually help you minimize all pairs, all ij pairs. So what I will do is I will just iterate on all ij pairs and I will try using this new edge added, can they be minimized or not. Simply, as you saw, this was existing value. I'll simply use that, okay, currently this 0 to 3 path was infinity. So with the new edge added, can I minimize it? Okay, I to j, it was actually infinity earlier. So currently what I will try is I will try from I to the new node, which is actually v is actually a 1, so you will see that it's a 1 here. Then from u, and then from v, which is actually a 3, to the j node, which is actually a 3 again. From I to u, then v to j, and also the cost will also be added because it is a path right now like this, right? So the cost also will be added. So the new cost will actually become a 6, which is less than infinity. So I'll just simply put this infinity here. So you saw that I will just simply try for again all ij pairs, right? And that is how you can simply, as soon as you add an edge, you will try for all ij pairs, which will actually make sure that you are using O of v square for all. For every added operation, you are using O of v square operation. So that is it. Let's quickly see the code. It's going to be pretty simple as we discussed earlier also. The main thing is in building the graph and in adding the edge. When I'm just calling shortest distance, it will be simply O of 1 operations. If it is inside my matrix, having a value less than int math, which is actually 1e9 for us, okay, that's actually a good. We have a value. If not, then sorry, bro. I'm really sorry for you. Cool. Then what we will do is in this, we'll just simply iterate on the graph as we had earlier. Adjacency list. Right now we'll have a matrix. So matrix of size n cross n matrix. Simple as that. Now I just simply go on to all of my edges as you saw initially also. I just firstly put in all of these values which were actually from my graph itself. I just put in all the values which were from my graph itself, which are the blue values. Cool. Then I will just simply place a 0 for the each equal nodes, which means from 0 to 0, 1, 0 to, sorry, 1 to 1, 0, 1 to 2 to 2, 0, and 3 to 3, 0. Now, when this is done, I will try to minimize for all possible ij combinations with this k as the middle node. Again, for all possible ij combination with this k as the middle node. Now, when this is done, again, that will be simple as we saw in the code also. Now, this will actually be operation of O of v cube, as you saw, hence v square here and a v here. All middle nodes, v nodes, or combination of ij, v square. So, building a graph itself is O of v cube, right? That's pretty much it. Cool, no worries. Now, if I want to add an edge, I'll simply, as I showed you, that I will use this u and v and the cost, and I will try to consider this as a middle node, and I will try for all ij combinations, and I will try to minimize the minimum distance for those all ij combinations. So for these ij combinations, I'll just say, just simply go and minimize it. Ij combination, current ij combination, I to u, then v to j, and cost from u to v is actually this cost. So I'll just get this cost, and with this you will see that, okay, it's for all ij pairs, so it's v square, but you will call this add edge n times, so it is n into v square. Again, space is O of 1 because you are not using any extra space, you are using a simple existing matrix itself. Shortest path, that is the best part. Now the shortest path call is just simply checking inside the matrix itself if you have a value or not. If you have an intermax value, like return a -1 because you don't have a distance between them. If you have a value, just simply return that value, and that will be a O of 1 operations, but you are having m calls to shortest path, so it is O of m. And space is also O of 1 because no other thing is being added. Now you will see that this will for sure work when m is equals to 1e6. If you wanna call your m as many times as possible, you can call, which is 1e6, you can still get it done. But if you will see that, okay, if your n goes 1e6, it will not work because your v is actually again 100, so this will not work. So you saw the previous would work if your add edge operation is high but shortest path operation is low. This approach will work if your shortest path operation is high but add edge operation is low. In this problem, both of them will work because both of them are low. That's the reason I just discussed both of the problems. Cool. The time is O of m and it is O of n into v square, and again for this v cube to build the graph, add edge and a shortest path, and this is ultimately of v square for entirely building the matrix itself, which is the grid. Cool, that was pretty much it. The video has gone 30 minutes, but I wanted to discuss both the approaches because I wanted you guys to know in the interview you can tell everything, why this is useful, why this is not, why this is useful, why this is not, and that's the main point. Simply solving by any way is not the point of an interview. Cool, thanks for watching. See you again. Bye bye.